everyone, this is your introduction to geometry, and there are a few theorems and facts that you need to know that come right from junior cert geometry actually. And vertically opposite angles are equal. So if you see the X shape, and I will try and point out to you the types of shapes you might see that would give rise to equal angles. So that X shape gives you vertically opposite angles equal to each other. If you see the Z shape, that gives you alternate angles. They're in the little kind of nooks of the Z. And then also watch out for the backwards Z shape. Those angles are also equal to each other. And they're called alternate angles. And every time you have to give a reason as to why two angles are equal to each other, you want to give one of these reasons: vertically opposite, alternate, corresponding, whatever the reason may be. Now let's see. So next we have corresponding angles. Note you get alternate angles and corresponding angles when you have parallel lines. So watch out for that. Parallel lines. All the angles here that are equal to each other. You have F and B, they're in corresponding positions. A and E are in corresponding positions, etc., etc. So they are corresponding angles. Now this theorem here, which again you had it from junior cert, the angle at the center of the circle is twice the angle at the circumference standing on the same arc. Okay, now I have three different diagrams here. Example 1, 2 and 3. I think example 1 is the one that might be most familiar to you, because you kind of see that paper airplane shape, and the angle at the circumference is twice the angle at the center. And watch out for angles at the circumference that might look a little odd, but see that little X out there? It's standing on the arc AB, and hence it is half the angle at the center. Now moving down here to this example 2, the arc AB here is a full semicircle, okay? So the angle standing on that arc is an angle at the circumference, and then the angle here at the center is 180 because it is a diameter. So the angle is a straight line. So half of 180 is 90. So what this gives us is that angles at the circumference standing on a diameter are right angles, and that's very convenient because it gives you a right angle triangle there. If you call that X, AXB is a right angle triangle. And then up to example 3 here, this is the odd looking one. So the arc here AB, which you can barely see, the arc AB here is greater than half the circle. So this angle at the center is a reflex angle, but it's still there. That's the angle at the center, and it is it's twice the angle at the circumference standing on that same arc. So just watch out for those. Congruent triangles. Two triangles are congruent if they share side, angle, side, angle, side, angle, side, 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 and a right angle triangle, right angle, hypotenuse, and a side. So if two triangles are congruent, they have the exact same shape and size. If two triangles are similar, they have the same three angles. So if they have the same three angles, they are similar. And watch out for a line drawn parallel to one side of a triangle. That gives you similar triangles because of the parallel lines. You've got corresponding angles, and then you've got a shared angle. Now, if you have similar triangles, I would immediately write down the three ratios that gives you that are equal to each other. So opposite the yellow angle, the little dot there, we have, and I label it as such, there's my little yellow dot, I'd write the two sides that are opposite it, X, Y and BC. And then for the green dash, the two sides that are opposite the green dash are AY and AC, and opposite the red angle is AX and AB. And watch out that you're consistent here in writing down these ratios. And what we have is the small triangle over the large triangle. Sometimes I write that even to remind myself so that halfway through I know which side is going on top. And I would write those down so that then you have that information and you don't have to be thinking about it in the middle of the question. Okay, then on to the three theorems that you need to know, and the proofs are in the drive along with the recorded proofs. Theorem 11, if three parallel lines cut off equal segments on some transversal, then they will cut off equal segments on any transversal. So watch out for that if you have three parallel lines, and if you have a line going across like that red one, ABC, if AB is equal to BC, then if you draw any other line across, it will divide that line into equal pieces. DE is equal to EF. And it's not the case that like AB is equal to DE or anything like that. It's just that within the one transversal, the parallel lines are dividing it into equal pieces. And theorem 12 here, absolutely. Theorem 12 here is a line drawn parallel to one side of a triangle divides the other two sides in the same ratio. Very much related to what I said earlier about similar triangles. So you've got ratios. So for example, like if AY, for example, was 4 and YC was 2, then maybe AX is 1 and XB is 2, or the other way around. AX is 2 and XB is 1, you know. They divide, a line drawn parallel to one side of a triangle divides the other two sides in equal ratios, but not necessarily equal length. It's just the ratio 2:1 is the same as 4:2. And then finally, theorem 13, if two triangles are similar, their sides are in proportion to each other, which we mentioned above. Okay, so you need to know the proofs of those 3 theorems. And then just along with this, tomorrow we'll be talking about geometry, area and volume. And you'll notice here, most of what I've written about area and volume relates to cones. They're the ones that are probably the trickiest. So one big fact about cones is that when you cut open a cone, so suppose for example, I cut open the cone along that luminous green line L, okay? If you do that, it'll open out to a sector. So imagine taking a party hat, cutting up one side, it opens out to a sector of a circle, okay? Now you want to match what pieces get mapped to what. So L, that was the side of the cone, opens up to a radius of the circle. So there's your L. And then the circumference of the top circle in the cone becomes the length of this arc here, the red. So basically colours correspond. Red turns into red and green turns into green. But remember that the circumference of the top circle there in the cone, that is given by 2 pi r, okay, where r is the radius of the cone. The circumference of the cone turns into the length of the arc of the sector, which we know from the log tables is theta over 360 2 pi L. So the slant height L there is the same as the slant height up there. So it's all summarized here. So 2 pi r, where r is the radius of the cone, is theta over 360 2 pi L, where L is the slant height of the cone. You know, you don't necessarily need to remember that, but just remember the relationship, maybe be able to draw a picture. Another thing about cones is that, which comes up often, is that you have a right angle triangle when you have a cone. The radius, the vertical height and the slant height all satisfy Pythagoras' theorem, so that's something to remember. And then also with cones, and this pops up a good bit, you have similar triangles if you have a cone and then maybe you fill it up with some quantity. I here had a cone of height h2, so that's the big H2, and radius r2 is filled up with liquid up to a height of h1 luminous pink and radius 1 luminous red pink again. So you could fill a cone, I don't know, in previous exam papers they've had a cone filled with grain, you could fill it with water. That gives rise to similar triangles, the black triangle and the pink triangle. Because the pink triangle, the line there is a line drawn parallel to one side of the black triangle, so it gives rise to your similar triangles, which gives us that h1 over h2 is equal to r1 over r2. That could be a handy fact to know.